Hello, this is Raymond and Marcus Chan's EC 4122 Advanced Programming Techniques final project for fall 2021. This course is called Advanced Programming Techniques and is taught by Dr. Hurley. So our project can be found at this GitHub. It's github.com JRAY810 /EC4122 _ traffic sim. All the code is here, and we can take a look at the README file to see what it's all about. So what our project is basically a simulation of a four-way traffic intersection and a measurement of that traffic flow across the intersection. And this project was inspired by MIT's Sensible City Lab. This is a project back in 2016. Basically, they had created a simulation where hypothesizing the idea of with autonomous cars, you can create like a slot-based system such that each car has its own slot and it would never collide with another car, so that no cars would ever have to stop at an intersection. They could just adjust their speeds and make sure their slot doesn't intersect with another slot. So we basically tried to make something similar, and we made a version simulating stop signs and a version that was technically fully autonomous. Video process demonstration is this video. It'll be coming out soon. The project is made in C++, and we used Ubuntu 20.04 terminal on Windows subsystem for Linux to compile it. So you need a G++ compiler, and you also need OpenMP and SFML. I believe it's SFML 2.5. And obviously for graphical support, you're going to need to install some SSH server or something to display the graphics. I personally have Xming installed. And yeah. So we're going to walk through the commands on this page. So to begin, I have my terminal here. And so we're going to compile it first. So to compile the simulation, you basically go to the head folder, so basically in this folder, and here you can see that we are in this folder with all the items with the make file here. So what we're gonna do is all you have to do is just run make, right? And if you want to do it yourself and see what it's doing, you can look at the make file, or you can look at this long compile list. It's basically compiling all the code in the code folder, the SFML display as the main function. You got your thread, your OpenMP, and all the SFML graphics, and then our executable called traffic sim. But our make command in the make file does this. So all we're gonna do is just run make. And then it will take a little bit because our code base is pretty large. It's got a lot of lines of code in it. So we'll go look at something else. Let's do that. Yep, it's done. And if we check in the folder now, there's a traffic sim executable here. Okay. To run the simulation, you have to make sure you start your Xming first. So find my Xming. Nice. Check that it's started. It's running. You're gonna have to run this export display command to make sure that it's exporting the display. So now it's done that. And then you can just run the executable with /traffic sim. So /traffic. There we have it. There's our simulation. And so this is by default the autonomous version. You can see our vehicles are just running through the intersection, and they're automatically scheduled so that they never enter the intersection at the same time as a vehicle with a conflicting lane. So for example, if a car from this lane is turning right and a car from this lane is turning right, they can both enter the intersection at the same time. But if a car from, let's say, this lane is going straight and a car from here is turning left to here, they cannot be in the intersection at the same time, otherwise that'll cause a collision. So it's just running automatically. Quick look, we've got a vehicles process count. It's basically counting how many vehicles successfully went through the intersection and then left the control of the traffic controller controlling this intersection. The average wait time is basically an average of the amount of delay each vehicle experienced when traveling through this intersection. So basically, there's a expected time it takes for a vehicle to enter the control of the traffic controller and leave the intersection, fully leave the control, and this is just an average of how much time it actually took minus how much time was expected. So like the average of the delay. And I believe, and this is measured in ticks. The program runs in ticks. You can set the ticks as you will see later. But yeah, it should take around 50 ticks to enter the intersection and fully leave the intersection. So we're gonna call this the intersection square, and this whole thing is called the intersection. And obviously, you just have to press the S key to exit the simulation. Okay. Quick look at the other actually we'll look at it later. Okay, so running the simulation. So the simulation has a bunch of flags. You can read the README file, but I will just demonstrate it for you here. So the quickest way to pull up all the commands is you run this help command, and it will basically give you all the commands you can do. So basically, the command line input format is your executable name. It could be traffic skim, or it could be something else, depending on what you did. And then you got 3 arguments. These are all optional, and every argument must come after the previous. So if I have a T argument, it has to be the second one right after traffic skim. If I have an R argument, it must be the third one, and there must be a T argument before it, and so on and so forth. And the most that we can have is like 4 arguments total. So the first argument, the T argument, is the traffic control simulation type. We have 2 of them currently fully running. So there's the autonomous simulation and the stop sign controlled simulation, so -A and -S. The traffic light control simulation is currently a work in progress. It's a lot more complicated than you think, because cars tend to wait very, very long if it's a single lane four-way intersection, because cars that want to turn left just have to keep waiting or something like that. And it's pretty difficult to simulate that, so we'll get to that eventually, maybe in another semester or so. The -R argument is the tick rate. So basically, this is the equivalent of time in the simulation. Each tick is a value that can be evaluated in microseconds. So you can input a value in microseconds to be the tick rate. By default, I believe this is, 100 milliseconds for each tick. And obviously, if you increase that value, the simulation will run slower, and if you decrease that value, the simulation will run faster. And the spawn probability, it's a percentage. It is a positive integer between 1 and 100, and by default is a 25% spawn probability. So basically, every iteration, it is checking to see if it wants to spawn a car, and this is the probability that it will spawn a car. Okay, so let's run a few of the commands to show you how they work. So obviously we first have the autonomous version, which is also the one that's running by default. You can see that they just run through. There's also the traffic light version, which support is not created for it yet, so it doesn't do anything. Obviously there's the stop sign version. You can see where the cars will stop at the stop sign before continuing through. Let's see. If we look at the commands again, we can adjust the tick rate. So remember, by default our tick rate is very fast. It's 100 milliseconds. So if I run a tick rate that's even slower, that means a huge number. So this is in microseconds. So 1 million microseconds is equal to 1 second. So this will tick very, very slowly, and you'll see the vehicles show up in a bit, but you can see they're traveling very, very slowly, and they will go wherever they need to go, do whatever they need to do, but it's really slow. And if I give it a 1 microsecond tick speed, from what I recall, this is really fast, and the computer might sometimes have trouble handling it, so it might look a little laggy. But yes, the cars are just flying by on the screen. You can't really see what's going on. But yeah, so that's the control of the tick rate. I personally like the 100 millisecond tick rate, and I think it's the best way to look at it. Although I think for the stop sign one, a slower tick rate is nicer, so you can see the car stop, and not just because they only stop for 3 ticks at a stop sign. Like, you're supposed to stop for 3 seconds at a real stop sign. I hope you all do. but yeah, 3 ticks is only 300 milliseconds, which is really fast, and sometimes it's hard to see. So that's that. We can now look at the third command line argument, and that's the spawn probability. So let's see, we have, we'll go back to our 100 milliseconds. I believe it's that. And then, oh, keep forgetting. 100 milliseconds. And then we have our spawn probability. So you can see, you saw that with 25%, it's not a lot of cars on the screen at the same time. But if I up it up to like 90%, there's going to be a lot of cars running at the same time on the screen. Let's see. Okay, so that's all of those. Oops. OBS. Let's see. So yeah, so those are the running instructions. Of course, if you always need help, you can go back to help. Our makefile commands, we've got make all, make testing, make clean, and obviously your normal make. Make is equivalent to make all. So if you make clean, it removes the executable, as you can see there. There's make. So you have make, and then there's like make testing, and basically those will create a testing simulator. And what this is used for, there's some test cases inside of the testing file that we use to test our code while we were building it. It's not comprehensive. There's just a little bit so that you can test some things. There's also a debug setup header file, and in there you can set the debug value to 1, and that will start printing everything. I believe if I run this, I believe my debug right now is set to 0, so we'll see a little bit, but that's all you get to see. All the rest of the stuff just doesn't show up. And this vehicle push to queue is provided by the testing simulator file. And if I turn debug on to 1, it'll print like a lot of things. And yeah, if you want to see where that is, it is, so there's our make file, debug setup. So here, if you set this to 1, it'll print. There's a lot of debug terminal outputs and console outputs in some of these files, and it will print everything for you so you can see what's happening. And if you for some reason cause a situation where the system crashes, or you're editing the code and something is going wrong, you can just look at the debug statements and hopefully you can figure out where the source of the error is coming from. Okay, with that, I don't know if there's much else. I guess known issue, our light control traffic controller. We have a file. Yeah, we have our light control traffic control file in here, but it doesn't work properly yet. We haven't really looked into creating it. It's got some traffic lights going, but the logic for determining where cars need to be is not there yet. Yeah, so we've just only implemented autonomous and stop sign control traffic. And that's basically it. This is created by Marcus Chan and me, Raymond Gia. We are part of the ECU department at Georgia Institute of Technology. And yeah, that's basically it. And obviously for quick display, I have our rubric, or our submission rubric file here. It's got the description, the contents, code repository. We'll add this video's link here soon. Marcus mainly worked on the graphical component. He made the SFML graphical implementation, as well as the stuff for displaying things. So for example, the lane and the intersection objects. He is also working on creating a version in OpenGL. And hopefully one day we'll be able to see a 3D version that's similar to the MIT version. I'll show you the MIT version afterwards. It's quite beautiful. I worked on the backend multi-threading part of this project, so that's all the multi-threading going on behind the scenes for the traffic controller that's controlling all the different pods and vehicles that are running through the intersection. And there was a lot of debugging involved. Yeah. Here's our little dinky rubric. We felt really proud of our project. So obviously there's the usage of our special topics that were covered in class. The two topics we chose were multi-threading SFML. You can see SFML with all the graphics. And for multi-threading, we used the standard thread provided with C++ libraries. And we also used OpenMP. And it was used for faster iteration through this vector or this data structure that contained all the vehicles, and we want to update their positions quickly, so we use multi-threading to do that. Along with obviously the threads that are running in the background for controlling vehicle positions and stuff like that. User input to simulation, we wanted a minimum of 2, we got 3. These are basically the command line flags I showed you. Obviously there's the type of intersection, we can change the simulation seed, and we can change the vehicle spawn probability. And obviously the two happy things that we made are the stop sign simulation and autonomous simulation. And one day we'll make that light traffic controller, and along with that we can make all sorts of great things like multi-lanes and stuff like that. But we saw that vehicles reached the intersection and they stopped, like stop sign rules, and they went on through before going on through. And for the autonomous version, everybody was just running through and there was no conflicting paths in the intersection square at the same time. Yeah. I also hope one day that we can make a cleaner display. Right now everything is moving so quickly through the screen, and obviously even when we slow down the simulation you can see that the math behind is calculating pixel positions on the screen that are quite far apart, and obviously because everything we're seeing, all the vehicles are almost identical. They are rotating, you just can't really tell. But yeah, hopefully one day we'll be able to actually put cars on the screen and make it look cool. If you're wondering what the heck those cars were running across the screen, oops. If you're wondering what they were, those are the infamous spherical cows in the scientific community. You can assume the cows are spherical. But yes, we have a bunch of spherical cows acting as our wonderful autonomous cars running through the intersection. Yes, spherical cows. And yeah, that's it. That's it for our final project. Hope you liked it.